Hi, this is Clayne Jones. I'm MSU's Extension Soil Fertility Specialist. Today I'll be talking about soil fertility and fertilization as part of the Farm Management FSA workshops. If you have any questions after this presentation, please feel free to give me a call at the number shown on your screen, 994-6076, or send me an email at clainej@montana.edu. So today's topics include discussing soil properties' effects on nutrient availability, deciding which of those properties you can influence versus which were simply handed to you and are part of your natural system. Third, discuss MSU's economic nitrogen rate calculator. And fourth, talk a little bit about fertilization, timing, and source. So in general, soil is composed of about 50% minerals, meaning the sand, silt, and clay that have been broken down from rock to form most of your soil. Only about 2% of soil is organic matter. However, that 2% controls a vast majority of the function of soil, and I'll explain why later. Generally, soil might have about 25% air and about 25% water. This is a graphic that shows as soil texture increases from a clay up to a sand, from basically something that's invisible to the naked eye up to something quite a bit larger. Water and nutrient holding capacity decline. So as probably makes sense to you, as the soil texture increases, it cannot hold as much water or as much nutrient. If you're interested in the fraction of sand, silt, and clay on your farm, you can either send your soil in for a laboratory procedure called a hydrometer test, which measures texture, or you can measure soil texture yourself using a mason jar filled partway with soil and then adding some water, and the instructions for that test are shown at the bottom of your screen. Sand, of course, has large pore space, low surface area, and low water and nutrient holding capacity, where clay is essentially the opposite. An ideal soil wouldn't be either of those because sands don't hold water, clays end up ponding and don't allow very much air to penetrate to the roots, as shown in that photo. So ideally you would have a mix of sand, silt, and clay, somewhere between a loam and a clay loam, or approximately equal parts of sand, silt, and clay form a very nice soil for farming. The next topic is pH. So as shown in this diagram, pH ranging from 4 up till 9 dramatically affects soil nutrient availability. So what's shown here is a wider bar means that there's plenty of nutrient availability. A narrow bar shows that there's not much nutrient availability. So for example, nitrogen availability really drops at low pH, partly because microorganisms responsible for making nitrogen more available in the soil and breaking down organic matter don't do very well below about pH 6. Phosphorus has this pinch point up here around pH 8, which is somewhat common for a lot of Montana soils. Phosphorus likes to bind with calcium, and calcium levels are high around pH 8. For pHs a little more typical in Montana now, somewhere between about 6 and 7.5, generally phosphorus availability is okay. Micronutrients like iron and manganese and boron often are less available at higher pH and more available at lower pH. The exception to that is molybdenum, which is the exact opposite. So in low pH or acidic soils, which are becoming more common in Montana, we might see nitrogen and phosphorus deficiency, maybe sulfur and calcium, magnesium problems, generally not micronutrients though. At more typical soil pHs for Montana, more like 7.2 up to maybe 8.3, again, generally we have a good availability of most nutrients, but we can see problems with micronutrients like zinc and sometimes a macronutrient, phosphorus. So as I mentioned, pH is generally high in Montana soils. It can decrease with elemental sulfur, but that's likely not economical for large acreage operations. Fertilizing with ammonia-based fertilizer lowers pH over time. And if pH is low, you might consider liming or possibly tillage to bring up higher pH soil lower down in the soil horizon. And crops tolerance varies with species and variety to low pH. So for example, alfalfa is not very tolerant. It starts having problems below really about pH 6, primarily because the rhizobia that form on alfalfa roots do not do well below about 6. Barley's a little more tolerant, somewhere around below 5.3 we start seeing problems with barley, below about 5.5 for pea, and depending on the tolerance of wheat to low pH, somewhere between 5.1 and 5.4. We've observed pHs as low as 3.8 in pockets and fields up in the Golden Triangle, so these pHs are these are tolerance thresholds, and we are seeing pHs below these levels on some Montana fields. So what's cation exchange capacity, or CEC? It's the parking spaces for nutrients in a soil. So most soil particles, what we call clays in soils, have negative charges. That allows positively charged nutrients like ammonium and potassium to get attracted to that soil particle, but not that strongly, meaning these nutrients, these positively charged nutrients, can come off fairly easily and get used by crops. And that's why we consider a soil with high cation exchange capacity to be a relatively healthy soil. So CEC is the total negative charge on the soil. A high CEC soil, somewhere around 15, has the capacity to hold nutrients with positive charges. Soils with large surface areas, such as clay and soil organic matter, have much more cation exchange capacity than, say, sands or silts or low soil organic matter soils. What else might high CEC soils hold on to? Herbicides, which might be good if you want some persistence of a herbicide. That's, say, a soil applied herbicide. It might be bad if it ends up increasing the rotation interval for a certain crop because it doesn't break down if it's held onto the soil. SOM stands for soil organic matter. What does soil organic matter do for the soil? Well, it does a lot of things. But one thing that it does really well at is holding water strongly. So this is a graph that shows the soil organic matter increases from 1% up to 6% for a sand, a silt clay loam, and a silt loam. The available water holding capacity increases dramatically. So for example, for silt loams, from somewhere around 12% up to 30%. That can be huge, especially for crops such as winter wheat, which really rely on stored water. As that soil organic matter decomposes, it also releases nutrients that's bound in the organic matter. So soil organic matter holds water, and it also provides nutrients to the plant. So changing soil organic matter is not overly easy. Think to yourself how long you think it might take to increase soil organic matter from 1.4% up to 1.5%. Well, it takes a long time. So this is a study done by my colleague Rick Engel showing the soil organic matter content in tons per acre in the top foot of soil in a long-term study conducted at the Post Farm near Bozeman. What this shows is for a number of different cropping systems: tilled fallow wheat, no-till fallow wheat, continuous wheat, pea grown for grain followed by wheat, pea grown for forage followed by wheat, pea grown as a cover crop followed by wheat, and then CRP. This is a 10-year study, so in 2002 the soil organic matter was about 28 tons per acre. By 2012, 10 years later, in the best cropping systems, which were the continuous wheat and pea grain grown for wheat, and then CRP, Conservation Reserve Program. Notice the soil organic matter only increased by about 1 ton per acre. That works out to be a difference of 1.4% going up to about 1.5%. So it took 10 years to have that small of an increase. One take-home message of this graph is that fallow loses soil organic matter. Hay or heavily grazed pastures may be maintaining soil organic matter, but as shown here, this pea forage wheat system is just barely maintaining the soil organic matter over 10 years. So on to soil nutrients. There's 14 mineral nutrients that have been found essential for growth of most plants. And by mineral nutrients, I mean those that come from the soil. Plants need 3 other nutrients that aren't considered to be mineral nutrients. Those are carbon, hydrogen, and oxygen that plants get either from the air or from water. But those are things we don't have as much control over. We do have more control over these nutrients because we can add fertilizer, for example. The nutrients are broken into 2 groups, macronutrients. There's 6 of, ranging from nitrogen to magnesium. The micronutrients, there's 8 of, ranging from boron to zinc. The ones that are shown bolded in red are ones that I or others have observed nutrient deficiencies of in Montana, so I'm only going to focus on those today and not the ones that we've never seen deficiencies of. Thinking about nutrient cycling in general, one way to think about this fairly complicated diagram is to focus on the gains that are shown in blue, like nitrogen fixation, deposition from the atmosphere, conversion of organic material over to available nutrients in a process called mineralization, and then also weathering of rock and soil. So those are all really gains. The losses would include harvest, erosion and runoff, volatilization, precipitation, a fancy word for the formation of a mineral, and then leaching. So in the agricultural world, our goal is to increase the additions and decrease the losses with the exception of harvest, where we generally want a high amount of harvested crop. So how do fertilizers fit in? Well, it would depend on the source where those fertilizers are going to appear, either at the surface or possibly some sort of long-term or slow-release product down here placed in the soil. So this is a table that shows available nutrient gains and losses. This first part of the table focuses on losses for nitrogen, phosphorus, potassium, sulfur, and micronutrients, and basically shows that harvest and erosion and runoff occur for all of these, but leaching only occurs for a few of them. So nitrogen, not much potassium, sulfur, boron, and chloride, not all of the nutrients will leach, and phosphorus sticks so strongly to the soil it generally does not leach in Montana. Only a couple of the nutrients volatilize, or meaning escape as gases to the atmosphere, and those would be nitrogen and sulfur. And then only really nitrogen gets immobilized, meaning gets bound in really high amounts by microbes. Certainly microbes need phosphorus, potassium, sulfur, and micros, but nitrogen's the main one that they essentially consume. And then phosphorus is the main nutrient that really can precipitate, generally as calcium phosphate minerals in Montana, and then also some of the micronutrients, copper, iron, manganese, and zinc can also form minerals. The gains, all of the nutrients can appear from mineralization, meaning decomposition of organic matter. Everything but nitrogen can come from rocks. Nitrogen is so soluble it does not exist in rocks. And then nitrogen is the only one of the nutrients that can come from the atmosphere and then get fixed by legume crops like alfalfa, sainfoin, pea, and lentil. So in summary, nutrients need to be in the right form to be plant available. Nutrients cycle among different forms in the soil. Soil characteristics influence nutrient availability. Many soil properties cannot readily be changed by management, and soil organic matter is one that can be changed and does have a large impact on soil nutrient availability, but is very hard to change. So now on to calculating fertilizer rate. So when trying to figure out how to know what to add to your soil, there's 6 questions to ask yourself. One is, which elements do you need? How much should you apply? What type of material should you use, or the source? Which application method is best, meaning putting it on the surface or maybe putting it down in the soil? When's the best time to apply it? And will I get a return on my investment? To know how much to apply, you need to soil test at least occasionally. You can't know how much to add if you don't know what's in the soil. So this can help you identify a nutrient deficiency or imbalance, can help you calculate fertilizer rates, can increase yield and or save on fertilizer costs. And I would suggest it's best done in the early spring because that's the best representation of your growing season nutrient availability. And if you want more information, there's a couple Mont guides that I have online on the MSU Extension website and also on my website, which is shown on the last slide if you want additional information. So what should you look for on a soil test report? Well, of course, nutrient content. That one's obvious, but maybe a little less obvious is certainly soil organic matter. If you have a very low organic matter, meaning less than about 1%, then you really need to minimize the amount of bare soil, switch to something like a recrop, or maybe even better yet, a perennial forage system. And you might have to add legumes to your system to try to build up that organic matter. If you have greater than 3%, then you can take what's called a nitrogen credit and you don't have to fertilize with as much nitrogen. I would also really look closely at soil pH. If you have less than a soil pH of 5, you probably have some metal toxicity, aluminum or manganese. If you have less than 6, you're probably observing poor establishment and maybe poor nodulation of legumes. And if you have greater than 8.3 pH, some nutrients like phosphorus and metals will likely be tied up. You likely have high sodiums, and you probably have some what's called soil structure problems where your soil probably doesn't drain very well. You might have some ponding and some shrinking and swelling of soil. The last 2 things I would look at would be soluble salts, which is sometimes abbreviated EC for electrical conductivity. And that should hopefully be less than 4. If it's greater than 4, that's considered to be a saline soil, which likely exhibits water stress and might have some problems with nutrient uptake. Soil texture and cation exchange capacity are not generally measured by laboratories, but they can be requested, and as I mentioned earlier, they'll affect water and nutrient holding capacity. So how much fertilizer do you need to apply? Well, some labs will provide a recommendation if you provide a yield goal, or you can use Montana guidelines and develop your own recommendations or guidelines. You can estimate the amount of fertilizer needed based on soil test results and crop yields, and I have a number of MSU bulletins that show you in table form how much fertilizer to apply for the major Montana crops. I now want to move on to economics and the law of diminishing returns. So the law of diminishing returns basically states that as a nutrient increases, say in this case applied nitrogen, it increases for every, say, 10 pounds of nitrogen added, the yield diminishes. That probably makes sense to you, and at some point it flattens out. At some point later it probably goes down a little bit. So the greatest yield increase per pound of nitrogen added is when applied nitrogen levels are low, and additional nitrogen did not produce any additional yield when nitrogen levels are high. In this case, the nitrogen needed for maximum yield is somewhere around 200 pounds of nitrogen per acre to attain 80 bushel. But as a farmer, you shouldn't be focused so much on maximizing yield. You, of course, should be focused on maximizing profit or net revenue. So this graph shows again a couple different curves where net revenue is plotted in dollars per acre. So this is net revenue above fertilizer costs. And what it shows is a couple different situations. So this is the net revenue for a low price and low cost scenario. So basically $3.50 per bushel, about the price that people were getting for winter wheat just last year in Montana in 2017 actually. And then when we have low prices, often nitrogen cost is fairly low. So 30 cents per pound of nitrogen, or somewhere around $300 per ton of urea. The second scenario given is a high cost or high price scenario where wheat is going for $7 per bushel and the nitrogen costs about 50 cents per pound. So backing up, remember that the nitrogen needed for maximum yield was somewhere around 200 pounds of nitrogen per acre. But in this low cost scenario and low price scenario, the best economic return is somewhat less than that, somewhere around 165 pounds of nitrogen per acre. In the high price cost scenario, it's better to apply a little more nitrogen, somewhere around 175 pounds of nitrogen per acre. So basically shows you that you'd lose a little bit of profit if you shot for this optimum yield. The other thing it shows you is that when prices and costs move up, you really shouldn't apply a lot more nitrogen. And when prices drop, you probably shouldn't apply a lot less nitrogen, because the best profit is not very different between these two scenarios, and generally nitrogen cost and grain price move together. Not always, but often. If we look at MSU guidelines of applying 2.6 pounds of available nitrogen per bushel, the applied nitrogen for winter wheat would work out to be about 170 pounds of nitrogen per acre, or very, very close to the maximum profit shown here. That was when protein discounts were relatively low. In this scenario here, we have relatively high protein discounts. So here again, the nitrogen for maximum yield was 200 pounds of nitrogen per acre. But the best economic situation with high protein discounts is to apply somewhat more nitrogen to really chase that protein. So at the low price scenario, this model at least predicts applying somewhere around 250 pounds of nitrogen per acre will optimize profit. In this higher price and cost scenario, the optimum nitrogen rate is somewhere around 200 pounds, or about what the maximum yield was. And of course, it's not quite that simple, which is why I and my colleagues over in ag economics have developed an economic calculator to determine the optimum nitrogen rate. And what you need for that calculator is the nitrogen fertilizer cost, the grain price, the estimated protein discount and premiums, which I realize we don't always know at the time of fertilization, but we can use recent averages, and maybe at some point we'll be able to better predict those based on weather patterns, especially weather patterns in, say, Kansas and Oklahoma, Oregon and Washington, places that all grow wheat, and their weather affects protein discounts and premiums because weather affects protein. You also need yield goal, and residual soil nitrogen, and soil organic matter. Calculators for barley, spring wheat, and winter wheat after fallow are all online at this link. So let me take you over to that. So this is what that link will look like. You can look at the introduction. You can, for example, look at the winter wheat graphic. And on here, it shows you what can be adjusted. So you can change soil nitrate, and you can see how that affects your curve. You can change soil organic matter. You can change yield goal, wheat price. 498 is kind of the default that was in here last. Let's say that's a little bit higher. You can change the nitrogen price per pound, the protein discount, and then at the very bottom you can change the protein premium. And notice that each of those changes affected the shape of this curve, which is the net revenue, and it also affects the crop yield. So with these scenarios, with everything I have down here, let me go with a little more realistic organic matter, somewhere say around 2.5%. The pounds of nitrogen applied at max net revenue would be 55 pounds per acre, so right about here. But let's say, for example, that your discounts and premiums were to go down, like happened this year compared to, say, last year. Notice here now that the pounds of nitrogen to apply drops to 45 pounds per acre because you're not getting paid for that extra protein. So it goes down some, but it doesn't go down dramatically. And you can run these same scenarios for spring wheat fields and for barley fields. So if you have any questions on using this model, please let me know. I've run a number of different scenarios for winter wheat following fallow. And just to kind of show you how it affects the optimum nitrogen rate expressed as pounds of nitrogen per bushel. So I've run this at two different protein discounts, a 5-cent per quarter percent protein discount, which is somewhat close to average, and then a 10-cent, certainly a high protein discount for winter wheat. And I've run that at three different urea cost scenarios, $275 per ton, $460, and $740. So at this lower protein discount, more of an average protein discount for winter wheat, and a $460 per ton urea, the amount of nitrogen to apply per bushel works out to be 2.6 pounds of nitrogen per bushel, which just happens to coincide with MSU's fertilizer guideline. But if the cost of urea were to drop, then you can apply a little more for the best net profit. If it were to go up, it would drop down to 2.3 pounds of nitrogen per bushel. At this higher discount, you'd want to apply somewhat more nitrogen, which should make sense to go after that protein. So at $460 per ton urea, you'd want to apply closer to 3 pounds of nitrogen per bushel. And this is all based on certain assumption: $5 per bushel wheat, 80 bushel per acre yield goal, and 2% organic matter. But all of those will vary for your particular situation, which is why I encourage you strongly to use that economic nitrogen rate calculator, not to use this particular table. So the best way to maximize profit and maybe even stay in business is to adjust nitrogen rates based on costs, proteins, cost, prices, and discounts, and then to use the MSU calculator. So how might you adjust your nitrogen rate? Well, certainly selecting a realistic yield goal, Knowing what your prior crop was, if you leave a lot of stubble, you'll likely want to increase nitrogen because that stubble will tie up some nitrogen. If you grow a pulse crop, you can reduce nitrogen by taking a nitrogen credit, and if you grow a cover crop, you can reduce the nitrogen rate somewhat more. I recommend sampling in spring, again, because it's the best representation of the current growing season. If you do sample in fall, or your crop advisor samples in fall, you might have to think about whether or not nitrogen levels actually went up over winter or went down over winter. And that's hard to know, but in a really wet winter, they might go down. In kind of an average winter, they might go up because microbes are active underneath the snowpack. Another way to adjust nitrogen rates is to evaluate your past nitrogen management based on wheat grain protein levels. So basically, if spring wheat protein is above about 13.2%, you likely are maximizing your yield. If you're consistently below about 13%, you probably should add a little more nitrogen. The level for winter wheat is closer to about 12%, what I would call the critical level. And if you want more information on that, you can go to my extension bulletin shown here. Timing of fertilizer application will depend on the source. So there's readily available fertilizers that should be applied when your crop is actively growing or right before it's actively growing. Nutrients like phosphorus, potassium, and sulfur, which aren't quite as readily available, should be applied at or before seeding, where nitrogen can be applied up to about mid-tillering or maybe even early stem elongation. If you want to see some nutrient uptake curves, you can go to my website here, which shows you when crops are really taking up nutrients at a really fast rate. Slowly available nutrients like slow-release nitrogen, manure, rock phosphate, elemental sulfur take time to become available, so they really need to be applied well before they're needed, meaning in fall or maybe built up with prior crops. This is an example of a nutrient uptake curve that shows as plant growth increases from early leaf stage through tillering to stem elongation up to heading, that nitrogen uptake starts slow, really cranks, really takes off in tillering stage, is still pretty high at stem elongation, and really by heading has essentially flattened, because at that point the crop is simply redistributing its nitrogen to the grain and out of the stems and leaves. So the best time to apply nitrogen for yield would be from early leaf stage up to tillering. The best time to apply nitrogen for protein would be somewhere between kind of mid-tillering up to early heading. And finally, how can you manage your soil for healthy soils so that those soils will produce healthy crops for a long period of time? Well, first you need to know your soil properties and only add amendments and fertilizer as needed. Certainly avoiding compaction by reducing tillage and reducing traffic when that soil is wet, and increasing the organic matter content by minimizing fallow, possibly adding cover crops, using perennials when you can, and using moderate levels of grazing. And then maintaining cover whenever possible with either vegetation or with residue. So in summary, soil characteristics influence nutrient availability. Soil organic matter is key to healthy soils and plant production. And soil tests, the online economic nitrogen rate calculator, and assorted publications are available to help you determine fertilizer rates and timing to optimize your use of fertilizer and to optimize your net profit. And And with that, like I mentioned before, if you have any questions, please contact me at my phone number or email shown on the first slide. And you can also get additional information on my website.